Hi, and welcome to video 6 on statistical inference in this unit 4, topic 3 of specialist mathematics. We're going to talk today about extending the confidence intervals topic from math methods to our understanding of sample means and therefore how we can use them. So our sample mean, remember, we can use as a point estimate, and to get our sample mean we just sum, and that should have a sum in front of it. Sum our x and we divide by how many there are, and that will give us our sample mean, and we assume that our mu is approximately equal to x bar. So what I'm saying by that is you've got a population of 100,000 people and you want to know what the average height of that population is. So you take a sample of that population at random, 10 of them, and you get an average of 173 centimeters. And so we'll just make the assumption, this is a point estimate. We assume that therefore the population mean is 173 centimeters. Pretty boring way of doing it, and also it doesn't give us the ability to talk about how confident we are in our answers. And it's the one that most people do refer to, but we want to take this a step further and introduce confidence intervals. So recall with a confidence interval, first of all, our 68, 95, 99.7 rule. So if we use a z-score of 1 or 1 standard deviation above and below, we know that 68% of the data will lie in there. So this is technically called a 68% confidence interval. If I know my mu and my sigma, my standard deviation and my mean, then I can be 68% confident that a sample chosen randomly will lie within 1 standard deviation of that mean, and 95% confidence that it will lie within 2. Now, we flip this over a little bit. We have common confidence intervals, and our common confidence intervals are 90, 95, and 99. So in this case, we like 68 is not great, let's be honest. You don't want to be 68% confident of something. So we start at 90, and even 90 is not used that often. So if we want to be 90% confident in something, we're 90% confident that a value chosen at random from a set of data will be within 1.64 standard deviations of the mean. And if you move across, you can see 1.96 standard deviations of the mean is 95% confidence, and then 2.58 standard deviations of the mean will allow us to be 99% confidence, which is sometimes really important. And you don't have to remember those values because you can do this in your calculator. Inverse norm, we want the center of our normal distribution to contain 99% of the data, standard deviation 1, mean of 0, and we get 2.58 out. So there's our confidence intervals. It's really useful in cases where we're taking a sample and our sample size should be greater than 30 or the binomial equivalent. And if we do take a sample, keep in mind that we're now moving to that idea that we don't know the population parameters, we only know the sample statistics. So if we take a sample, we're going to assume that the mean is approximately equal to the population mean, so the sample mean. And then we're going to look at how confident we are of that, but we are going to have to assume that the standard deviation of our sample, which is sometimes called S, is approximately equal to the standard deviation of our data set. And again, if our sample mean contains enough data, this is usually a fairly good estimation to make. But of course, we know that when we take a sample mean, our standard deviation compresses, but we can reverse that process because we can multiply out by root n. So let's have a look at this. If x bar is the distribution of the sample mean, then x bar is approximately normal with this sigma and this mu. So where we assume that S is equal to sigma over root n, you'll see all the notation uses that sigma instead of using S. So a 90% confidence interval will be x minus 1.64 times the standard deviation. In this case, the standard deviation is sigma over root n. And x plus 1.64 times the standard deviation, which is sigma over root n as well. And that will give us our 90% confidence interval. I'm assuming a little bit that you've done this in methods and you're comfortable with it. Now that said, obviously again, and this is a good discussion point, we've got our standard deviation is related to this sample size. As we increase n, then root n in the denominator will decrease, will increase as well. That'll get larger, which means the whole fraction will get smaller. That will decrease, which means 1.64 times that will get smaller, and our confidence interval will shrink. And that's good because we want to be more confident within a smaller range. That's the point. We've also flipped this on our head because we're now using this to predict the population parameters. So we're taking heaps of samples and we're not predicting with a confidence interval where a sample might lie. We're predicting that if we've taken enough samples, we are 99% confident that the actual population mean exists within this range. That's the key here. So it's quite similar to methods, except in methods we're dealing with the binomial probability. Now we're dealing with our sigma is something slightly different, but otherwise the same. So let's have a look. A publishing company wants to sell a new textbook. Research shows that the sample of 25, or research shows that in a sample of 25, the mean price was $145 and the standard deviation was $35. Calculate the following confidence intervals. So let's do this in order. A, to calculate a 68% confidence interval, which we talked about earlier was pretty useless. A 68% confidence interval requires a z-score of 1. Approximate. I'm going to use approximate because as soon as you see that 68%, you're thinking 68, 95, 99.7 rule. So you can use that z-score 1. And so our confidence interval will be equal to, and we've got our x bar or mu minus z times sigma over the square root of n to x bar plus z over sigma plus z sigma over root n. Now to n, just want to make the point here that root n is equal to 5 because n is 25, so let's just save ourselves a bit of time. And our standard deviation was 30, so we've got nice numbers, so 35. So therefore sigma over root n is equal to 35 over 5, which equals 7. And so our confidence interval in this case is 145 minus 1 times 7 to 145 plus 1 times 7. And so that's equal to 138 to 152. We are 68% confident that our population mean lies within that range. B is for a 90% confidence interval. Now we know our 90% data, and that is that our confidence interval will be equal to, I'll go straight to the numbers, 145 minus 1.64 times 7, 145 plus 1.64 times 7, and so we can do that calculation now. So I've just done 1.64 times 7, and now I'm doing the 145 minus my answer, because then it's easy to change the next bit. You get 133.52, and then I just go back up and change that to a plus, and it gives me 156.48. And you can see my confidence interval has gone from 68 to 90, but my range has widened. We need to have a wider range to be more confident. So that's all right, and our range for 98 should widen as well. Our confidence interval for 98 is equal to 145 minus Z98. Now I've done this deliberately because we don't know Z98. So what I'm going to do instead is I'm going to find it. It's probably unlikely you'll be asked to do one that's not a common knowledge, but you might be, and so you need to know how to find it. So I'll go back to my calculator here, and I'm just going to do an inverse normal. And I'm going to do it, well actually I don't know the syntax for that, so I'll go across to statistics, and then distribution, normal, inverse normal there. I want it to be central, I want it to have 0.98% of the data, sigma 1, mu 1, and I get 2.32 is my value that I'm going to use for my z-score. So this is equal to 145 minus 2.32 times 7, 145 plus 2.32 times 7, and I do that calculation quickly. I'm going to use my previous calculation, just change the 1.64 to 2.32, and I get 161.24, and on the below side I get 128.76, and you can see that we got an increase in our interval again because our confidence is raised to 98%. So there's example 1, and there's the start of our work here. So I'll leave this video here, and in the next video you can see already we'll talk about the margin of error. All the best.